For day 3, we're going to be introducing logarithmic functions. If you remember from Algebra 2 last year, we talked about the log function. It helps us solve and work with exponential functions. So this right here is going to be the most important thing you need to know about logarithmic functions, and that's converting back and forth between log form and exponential form. Okay, so if I have an example here, let's start with an exponential function. We know 2 to the third equals 8. Well, if I needed to convert to log form, I would take the equation, and because I'm going from exponential form, which has an exponent in it, and I'm going to log form, I have to have a log in it, and then the base of the log is always going to match the base of the exponent. And then the inside of the log is always going to be the answer of the exponential, and that equals the exponent, which is going to be the answer to the log form. Okay, so these two right here mean the exact same thing. It's just one is in exponential form and one is in logarithmic form. Just like a fraction and a decimal, 1/2 can equal 0.5. They both mean the exact same thing. They're just written in different forms. So we got to make sure we're able to convert properly. And then a couple other things, special logs, just like we had special exponential form with e yesterday. A log that has a base e is also known as the natural log. So if you see ln of x, that's the same as a log with a base e. And then if you see a log without a base, there's no base number there. It's not a 0. It's circled. That means that there is a base 10 there. It's implied. If there's no base for the log, then it has base 10. Okay, so a couple things, a couple reminders from logarithmic functions that we need to know. So again, the most important thing that we highlighted, and we did that example there, is what we're going to start with. So we want to write these in log form because we're starting in exponential form. So again, if we're going to log form for number 1 here, we're going to log form, so we have to have a log. Remember, the base of the log has to match the base of the exponent, so log base 5. Make sure you write it small. Do not write it big. It's not the same size as the letters of the log, because we have to have the inside of the log here. The base of the log matches the base of the exponent. Log base 5 of 1 over 125 equals that exponent, -3. Okay? So again, make sure that you are able to convert back and forth with ease between log and exponential form. And the way we're going to do that is go ahead and try these next 3 problems here and writing to log form. And then, so pause the video, try those 3 problems, and then unpause the video and check your answers and make sure that you're able to do so, right? If we look at these 3, again, the base of the first log is e, so I wrote it in that form that we did the first one. But remember, log base e, we want to simplify even more, because if it's got a base e, that means that it's a natural log. So we have this, the natural log of 1 equals 0, which actually is a property, so that's kind of just nice to know there. If you have the natural log of 1, that value is equal to 0. For the second one, we have the log base 5 of 6 equals x. And then for the last one, again, because there's a base e, it's the natural log of 8 equals 3t. And you can see right here why we have logarithms, because if we were trying to solve for x here, this would be a quick one-step problem. You know, we can't solve for a variable in the exponent. The way we do that, convert to log form, and now we actually have the value of x. This one, it would just take one more step, dividing by 3, to actually solve for that t value. So that's why we have logs. They're really helpful, especially when you have variables in the exponents. Now, reverse, we got to make sure we're able to go backwards as well. If we're starting in log form, we got to be able to go back to exponential form. So go ahead and pause the video, use the same properties but in the reverse order, and see if you can get those to exponential form. All right, so for number 1, if we check it out, remember the base of this log for a natural log is e, so the base of the exponent's got to be e, and then the other side is 5, so e to the 5th equals u. And again, like we talked about, this is really helpful because if we're starting in exponential form, but our variable is inside that log, well, now we just solve for u by doing a one-step conversion back to exponential form. If we take a look at the last one, they're all variables. B to the c equals a. So make sure we are good on converting back and forth between log and exponential form. Checking out the graphs of these log functions. I already started, so if you want to write that down, we already did the exponential functions yesterday. So I put it on there for you. Remember, the domain of all exponential functions are negative infinity to infinity. The range is from the horizontal asymptote, which is 0 to infinity for the base function. The y-intercept is 0, 1, and then again, the horizontal asymptote is y equals 0. If we're looking at the log functions here, okay, if we're looking at the log functions here, I'll show you the x-intercept is going to be at 1, 0. So there's going to be an x-intercept at 1, 0 instead of a y-intercept, like the exponential function. And because the exponential function has a horizontal asymptote, the log function is actually going to have a vertical asymptote. So x is going to equal 0. And then the domain, if we draw this graph, I'm going to show you what these graphs look like. For a log function, the graph's going to look like this. And the domain, because this is what our graph looks like, we have a vertical asymptote. The domain is from 0 to infinity, and the range is from negative infinity to infinity. And what you notice here, if you look at both of these base functions, the exponential and the log of x, if you look at both of these functions on the same graph and those properties that we talked about, the domain of the exponential matches the range of the log. And the range of the exponential matches the domain of the log. Well, remember, what does it mean if you have two functions whose x and y's are switched? That means that they are inverses of each other. And if you look at the graph, the way inverses look on a graph, it means that they are reflected over the y equals x line. So pretty in depth there, but basically what you need to know is that the exponential and the log graphs are inverses of each other. I know it's written a little messy over here, but that's what we need to know. So the exponential functions and the log functions are inverses of each other, which is really nice because now that we know these properties over here for the log function, we're going to go ahead and graph one right below. But since we now know the base function, we can just graph using transformations just like we did on the exponential functions yesterday and on day 1. If we take a look down, that's what we're going to go ahead and do. So for graphing y equals negative log of x plus 1, the first thing we want to do, we did it in blue, so I'm going to go ahead and graph this parent function. The base function for y equals log of x. So this is what the base function looks like, just log of x. And what we're going to do is we're going to apply all the transformations going on over here. So remember, if that a value in front is negative, that means we're reflecting over the x-axis. It's a vertical reflection. So because this point is already on the x-axis, it can't really reflect. It's going to stay in the same spot, but this line is going to reflect. So I'll leave that dotted. So that line is going to reflect. So that's our reflection line. But then we also have a horizontal translation. This means we are going left. Remember, opposite inside, left 1. So each point, which we only have 1 here, is going to go left 1. So this right here because it was at 1, 0. This is going to go left 1. And now that is our final graph. Once you're done, you can either really darken. It's kind of tough here because it's pretty tight together, but you can either darken your final line or just erase your dotted line. And that's our final graph. Now, remember, there is a vertical asymptote. So just because we moved the coordinates left 1, we also need to move the asymptote left 1 as well. So as we go ahead and fill this out, domain, because the asymptote shifted, the domain is now from -1 to infinity. The range is not going to change, but the x-intercept went from 1, 0 to 0, 0. And then the vertical asymptote is x equals -1. And then we already know the y-intercept because it's got to be the same as the x-intercept in this case because the x-intercept's at 0, 0. So tonight when you graph a couple of the log functions, again, use that parent function or the base function that we had up top, and you can transform it using all those transformations that we know about. On the back, we're going to go ahead and, that's the bottom. On the back, we're going to go ahead and find the domain of log functions algebraically. So we can look at a graph if we were able to graph it in order to find the domain, but if we don't have a graph or we're asked to do it algebraically, we got to be able to do that. So here's our note. The domain of a log function means the inside of the logs must be greater than 0. So if I take a look at this first one, we have the log by itself. The inside of that has to be greater than 0. So we set up an inequality greater than, not greater than or equal to, but greater than. And now we have to go ahead and solve this inequality. Remember, you guys learned this earlier this semester. Because this is a quadratic, we first got to find our key numbers. Key numbers. So make sure we are able to do that. The way we find our key numbers is we solve for this inequality. Well, if I divide everything by -1 on both sides, I need to flip the sign. The only reason I'm doing this is because it'll make it easier to factor in a minute. So now that I have that, I can factor x plus 2, x minus 1, x equals -2, x equals 1. And again, it is an inequality, so those are not our solutions. We have intervals we got to work with, but these are our key numbers. So thinking back to earlier this semester, what do we do with our key numbers? Well, our key numbers are the x values that cause that inequality to be 0. So we have to set up our intervals around those key numbers to see which parts cause that left side to be positive or negative. So we have -2 to 1, and then 1 to infinity. And remember, because you can technically use either one of these, but I'm going to use this one because it might be a little bit easier to plug in. If you want, you can use this one, but whichever one you do pick, you got to make sure you're really looking at the inequality sign, because if you pick the top one, then you're looking for your output to be positive. But if I'm looking at the bottom one, then I'm looking for my output to be negative. So if I plug in any number inside this interval, so let's go ahead and plug in -3. Well, -3 squared is 9, plus -3 is 6, minus 2 is going to be 4. So that's going to be a positive number, which means that's not what I'm looking for, because again, we're saying less than 0. If I plug in a number in this interval, we'll say 0. That's the easiest one. 0 squared plus 0 minus 2 is a negative number. That is in my interval because I'm looking for a negative number. And then if I pick 2, 2 squared is 4, plus 2 is 6, minus 2 is 4. That's again another positive number. We don't want that. So the domain for this function, because we set the inside greater than 0, the domain is from -2 to 1. So if we graphed that function with our calculator, it'd be too tough to graph with transformations because it's got a quadratic inside the log. But if we graph that with the calculator, we'd be able to see that the domain left and right would be from -2 to 1. For the second example, go ahead and pause the video, try it on your own, and then unpause the video and see how you did. We're finding the domain of that second example. If you're stuck, here's the hint. Again, we're taking the inside of this function, and we got to set it greater than 0. So if you're stuck, we set that up, and your key numbers after you're solving are going to end up being -3/2, and then 5. So if that helps you out, go ahead and pause the video again, and then finish it. If you're still good, here's the rest of the work. So again, we found those key numbers by setting up that inequality, and then we tested each number in those 3 intervals, and we found that the lower and upper end intervals worked. So that is our final answer. And that's how you find the domain of log functions algebraically. Moving on to the last part, which is finding the inverse of the given functions. The way we find inverse, remember, 2 steps really, that's it. We want to switch x and y, and then solve for y. And then just make sure that you use correct notation at the end. And that's about it. There's 2 steps, and then just make sure you use correct notation at the end. So if I want to do this, remember f of x is the same as y. So if I want to find the inverse function, switch your x and y. And then here's where the conversion between exponential and logarithmic functions really help. Anytime you need to get something inside of the log, out of the log, we can convert to whichever form we are not in. So we're going to convert to exponential form. So if I convert this equation to exponential form, I'm going from logarithmic, which has a base e, right? This is log base e for natural log. And I'm converting to exponential form. So the base of my log is going to match the base of my exponent. It's going to be e to the x equals whatever was inside that log. Again, you can see how important being able to convert back and forth is. But now, again, remember my goal is to just get y by itself. So by converting, now it's just a simple add the 1 over, e to the x plus 1, not in the exponent, equals y. And then make sure you use the proper notation. We used f of x. So f inverse of x equals e to the x plus 1. And that is your inverse of the original f of x function. For the second one, if you're feeling confident, go ahead and pause the video. Try this one on your own, and then unpause the video and check it. Otherwise, I'm about to unveil the work and explain it in a minute. So looking at the second one, here's the work. We'll kind of walk you through this one step by step. So the same concept applies. In this case, I did 2 steps in one, really. So again, this was y. So we switched x and y. That's how you find the inverse. But then the number one thing here, you got to be careful. The number one thing is you cannot convert to logarithmic form until you have the base with its exponent by itself. So this all has to be by itself before we can convert. So you first have to divide by 5. You cannot, and I repeat this, you cannot multiply these two. This is not allowed. This is not allowed. These are separate, so you got to keep them separate. Get the base of the exponent by itself. Now that I have a base to an exponent, I'm allowed to convert. So remember, the base of my log has to match the base of my exponent, and then the other side becomes the inside of the log. Now I have the y out so that I can get y by itself. So now once I get y by itself, we have the log base 2 of x over 5 plus 1. And then again, just to reiterate, once we add this 1 over, it has to stay on the outside of that log. These parentheses need to be there to close that log. so we know that 1 is not inside that log and not a part of it. And then just make sure at the end your notation is correct. Okay, so there's our intro to logs. We did a little bit of converting to make sure we're good on that. We graphed them using transformations. We found the domain algebraically, and then we found the inverses of these log and exponential functions. Okay, so go ahead and work on the homework. If you have questions, please do not hesitate to reach out to your teachers, and good luck.